What up? We out here in Chicago on this beautiful day, chilling on my back porch. And if you don't know why this man is famous, by the end of the video you will. Some know him as a scientist, a philosopher, an artist, or just an icon of genius with his crazy hair. However, if you haven't taken an upper level physics class, you might not know why he's deserving the title. Lucky for you, you don't need advanced mathematics to understand what he contributed. Before we dive in, let me talk a little bit about the philosophy of science. So according to Thomas Kuhn, scientific progress happens in 3 stages. The first stage is normal science, where research just happens under one paradigm or one way of thinking about the universe. Researchers just go into their narrow field and develop new techniques, methods, tools, and collect data. Everything is all good. This is a very productive stage in science. However, once enough data gets collected, over time, anomalies or disagreements begin to form within the paradigm. This is not cool. It puts our understanding of the universe in jeopardy and something new is needed. Thus, the third stage is a scientific revolution, or a paradigm shift, where a new way of understanding the universe comes in and makes research more effective and intuitive for the cycle to begin. Restart. So this to give you an idea about normal science in the late 1800s, Max Planck, a famous physicist's advisor, said that there's nothing more to be discovered in physics, only holes to be filled. Well, he couldn't be any more wrong. At the time, there was a disagreement between the 2 biggest theories in physics, and that was Newton's classical mechanics and Maxwell's electricity and magnetism. Classical mechanics is just concerned with the universe around us. So if a car is moving at 50 miles per hour and 2 people are playing catch, if the person moving in the car measures the ball to be 10 miles per hour, then the person in the reference frame outside of the moving vehicle measures the ball to be 60 miles per hour, because if the car is moving at 50 miles per hour, the ball is thrown at 10. 50 plus 10 equals 60. However, if you replace the ball with a beam of light, something else happens. Maxwell said that the speed of light must be the same in all reference frames. So the person moving in the car and the person outside the car will measure the speed of light to be, well, the speed of light. This is very weird because the car is moving. So the car can be moving at 100 miles per hour, 1,000 miles per hour, 1,000,000 miles per hour, and the 2 reference frames will still measure the speed of light to be the same. This doesn't make any sense at all. Imagine if you want, but you can't. Einstein was a very visual thinker, so the solution he proposed was the universe is 4-dimensional. Space and time are no longer separate things, but one 4-dimensional space-time, time being the 4th dimension. He also said, in his theory of special relativity, that the universe, or motion, is not absolute, but motion is relative instead. Newton came up with the idea that motion was absolute, and at the time, people disagreed. People wanted to think that Maxwell was wrong, because Newton, he was the father of physics at the time. So this just gives you an example of what happens when you go against a conventional line of thinking. In this theory, a property of it is distance remains the same between reference frames. And also weird things could happen, like length contraction and time dilation. So I'll show you one right now. This is most famously known as the twin paradox. So let's just say Mary and Sue are twins. And they grow up, and Mary gets sick of Sue, so she takes a vacation, she hops in a spaceship, and goes into space at the speed of light, close to the speed of light. Now, she comes back 5 years later, and what happens is she gets back and she sees Sue and the rest of the world much older than she is. Like while she aged only 5 years, they've aged 30 years. Now, this is very weird, but it goes against the way the way we think about time, our intuitive notions of time. However, this is the truth, and there has been experimental evidence. So, in order to get a better understanding why, I introduced something called a space-time diagram, where time is on this axis, and the 3 spatial dimensions are on the other axis. So, I mentioned earlier that distance remains the same between all reference frames. So these lines are about 16 inches each. So this line represents Sue's movement through four-dimensional space-time. She just moves straight up in the time direction because she's at rest. However, Mary is also sharing her motion in the space direction because she's moving. So, therefore, she moves less through the time dimension, as you can see. This is just simple geometry. This is how the universe works. Now, if she moves very close to the speed of light, what happens is time slows down so much that pretty much time freezes and an infinite amount of time passes in the rest frame, in the observer's frame of reference. So, this isn't a completely accurate representation because this isn't a completely accurate diagram because in order to have a correct representation, you need something called a Lorentz transformation. And that involves math. I'm not going into it now, but I put the link below, so you should check it out. So, another consequence of his special theory of relativity is E equals mc squared. If you haven't heard of this, you live under a rock. It's very simple to understand. All it says is mass times the speed of light squared equals your rest energy, an object's rest energy. So, for me, if I take all the mass of my body and times it by the speed of light squared, I get my energy at rest. To get my total energy, I take my rest energy, which is just mc squared, and I add it to my moving energy. So this term behaves pretty interesting because as your speed goes to the speed of light, this term goes to infinity. It's the same mathematics that I discussed before. As time goes to infinity as you get close to the speed of light, and it's Lorentz transformation, so you should check it out. A consequence of this theory is the atomic bomb. So, it's pretty sad. So, some historical scientific revolutions. So, before Galileo, people thought the Earth was at the center of the universe, and all the planets in the sun revolved around it. However, Galileo in 1615 said all the planets actually revolve around the sun. In that same century, Newton came along and said the same thing that makes apples fall to the ground is the same thing that keeps the planets orbiting the sun, and that's called gravity, which is just a force that attracts objects with mass. Many years later, Einstein said all gravity is just curvature in this four-dimensional space-time. And mass or energy is what curves space-time. Now, to give you an idea, because curvature in four dimensions is pretty weird, I drew this two-dimensional universe with this dude playing catch, and he understands all the physics that's going on. So, if I bend this paper, if I bend it, twist it, fold it, I can do whatever I want with it. Like, he's still gonna read the physics to be the same. He's gonna, the physics isn't gonna change because he can't see outside of the two dimensions, just like how we can't see outside of our three-dimensional world. But, so objects such as this GPS satellite move in a straight path, but because the space around it is curved, it goes into orbit. So, explain gravity. And this is the general theory of relativity, generalizing a special theory of relativity. So evidence about this came about on one solar eclipse where we looked out and we saw a star here, but actually the star was over here. So what happens is the sun has a strong gravitational field, or a law of curvature. So this star moves so the light emitted from this star moves in a straight line. However, because it's passing the gravitational field, it gets bent. And its trajectory gets altered. So we have to see the star here. Now this goes against Newton, because Newton said gravity is the attraction between massive objects, where the light is massless. So according to Newton, light shouldn't get affected by gravity, but it does. So Einstein's right, Newton's wrong. This is the proof verbatim. So this is an example of the sun curving space-time. Now, if you take all the matter, all the mass of the sun, and condense it down more, you get a stronger curvature, more curvature, and you condense that down more and more curvature. So the amount of curvature doesn't just depend on the amount of mass, but also the mass or energy density. So if you condense all the mass into a small enough area, a small enough distance to find by what's called the event horizon, what happens is all the mass collapses into a single point of space-time. And this makes a black hole. So everything that passes through this event horizon gets sucked into the black hole. Now, the event horizon is defined by your mass. It's just a radius where once all your mass gets condensed down, you form a black hole. So for me, if I want to make myself into a black hole, I need to condense myself into a much tinier region of space than the Earth does to make itself into a black hole. It's very interesting. Another consequence of his general theory of relativity is a wormhole. And that's when space gets distorted in a way that two areas of space-time, two regions of space-time comes together and forms into one. So there's like a tear and there's a hole that brings them together. So a wormhole is just, it would look like a three-dimensional sphere, and we step through it and we end up in another place in space, or we could end up in the future, the past. So this is the closest thing to time travel. Unfortunately, black holes are very unstable. Macroscopic black holes are very unstable because the throat of the wormhole, or the region connecting the two pieces of space-time, relies on negative energy. And that's a quantum effect that I'll talk about in the next video. But it's very hard to have it macroscopically. However, where you do see wormholes is in particle accelerators. So, such as at Fermilab or CERN, where they take small particles and they collide, they bring them very close to the speed of light, and they collide them together. So the particle's rest energy is very small because it's very tiny. However, as we saw earlier, since it's moving, it has a lot of energy. And when they collide, there's a lot of energy going into a very small region of space. So therefore, space gets distorted and creates black holes and wormholes. And this prevents a lot of scientific progress, experimental progress that we have now. It's very much a roadblock. So with these wormholes and the black holes, they evaporate very quickly, and they're not detrimental to our existence in this universe. Another interesting thing I want to talk about, which was recently discovered, was gravitational waves. So this is a pretty simple concept to understand. So as we saw, the mass curves space. So once a very massive object moves, this curvature of space flattens out and it creates just a ripple through space-time. And so we see this all over the place. It's kind of like another way to think about it is like a guitar string. So if we pull this down, this represents mass bending the string, which is space-time, and once we release it, it just ripples throughout. So the gravitational waves that we detected in LIGO about 1.5 years ago, those waves, goes from two colliding black holes. So what happened was, throughout the universe, it, as the gravitational wave passed us, we expanded and then shrunk. And thus it created a ripple. So this happens all the time. And yeah, it's a very interesting consequence. Thank you for watching. This has been fun. Hopefully you stay tuned for my other videos. I hope you learned a lot. Peace.